Welcome to Number Theory Divisibility. This is the first lesson in several lessons I will be preparing on the topic of number theory. I have two lessons on divisibility. This is the first of the two, and then I'll follow up with some lessons on relatively prime numbers, arithmetic progressions, prime numbers, and so on. So stay tuned for the full set of lectures. Most of the problems in this particular video are based on variations of problems from a book entitled, let me point to it here, 250 Problems in Elementary Number Theory by Wrocław Sierpiński. And you can borrow this book from the Internet Archive. It was published back in 1970, but it's still available for purchase if you are interested from Amazon. And I have a few, I think I have one problem actually that I made up on my own, and then the solutions are my own. I prepared solutions for the few that I selected here in this video. For each of the problems, I'm going to state the problem on one slide, and then you may want to stop the video if you're interested in trying to solve the problem yourself. And then typically on the next slide, or in some cases several slides, I'll give you the solution. Also, in some cases, I have hints. So I'll give you the problem, and then I'll show you the hint, which is typically on the same slide as where I have the problem, and then the solution would, as I say, be on the following slide or slides. So let's look at the first one here. This is relatively easy. They get harder as we go along. Find all n in n here. This means natural numbers. So I defined that down here. They're the numbers 1, 2, 3, basically the counting numbers. So find all natural numbers such that n squared plus 1 is divisible by n plus 1. And then divisible has a very special meaning in number theory. It means exactly divisible, so with no remainder. And we write it like this here: A divides B. That means A exactly divides B. And that means you can write B is a number times A. Actually, it could also be a negative number, but just giving you an example here. So 3 divides 12. 12 can be written as 4 times 3. Okay, so you might want to have a look at this, and then on the next slide I'll give you the solution, or at least my solution. The solution is fairly easy. We write n squared plus 1 is n squared minus 1 plus 2. Then we factor these first two terms here is n plus 1 times n minus 1, as you know from basic algebra. Then we divide n plus 1 into this, and we get n minus 1 plus 2 over n plus 1. And so this is, of course, always for any natural number n, this is always an integer, but this is only an integer for n equals 1. Remember, we had the constraint that m was a natural number, 1, 2, 3, 4, and so on. There's another solution. If we allow for negative integers, if we take minus 3, then the denominator here would be minus 2, and you would get a minus 1. But again, we were restricted in our question for n to be basically a positive integer. All right, we have our second problem. Find all x in z, and z is the standard terminology for integers. So this allows for positive and minus whole numbers. So find all x integers such that x minus 3 evenly or exactly divides x cubed minus 3. And I'm going to give you a hint in a second, so you may want to pause the video if you don't want to see the hint. Okay, and here's the hint. Consider using polynomial long division. All right, so I'll give you the solution on the next slide. So let's take use of our hint from the previous slide. We divide x minus 3 into x cubed minus 3, and I've kind of showing you the whole solutions here, but you go one step at a time. First, you see what's the largest thing you can multiply times x minus 3 and not exceeding this, or at least not exceeding this first term here. So we multiply x squared times x minus 3. We get x cubed minus 3x squared. We subtract this from here. We eliminate the x cubed. We get 3x squared, and we bring down the minus 3. Then we multiply 3x times this in order to eliminate this 3x squared, and we get 3x squared minus 9x. Then we subtract this from this, and we get 9x minus 3. We multiply this 9 times x minus 3 to get this here. We subtract, and we get 24. So the result of this means that x cubed minus 3 divided by x minus 3 equals this here, x squared plus 3x plus 9, and then a remainder of 24 divided by x minus 3. And then the problem reduces to when this is this 24 over x minus 3, when is this an integer? And these are the possible values. Let's just check a few of them. If we put in 0, we get minus 3 and a 24, that's minus 8. If we use minus 21, then we get minus 24 and the 24, and that's minus 1. I'll leave it to you to check the other ones here. And notice if you go beyond 27, you're going to start getting fractions, and if you go below minus 21, you also get fractions. And of course, there's some gaps in here where you will also get a fraction, like 12, for example. If you have 12 minus 3, that's 9. 24 by 9 is not 9 doesn't divide exactly into 24, so you get a fraction in that case. Okay, then I have an extra credit problem that I made up. Find all integers such that x minus 2 divides x cubed minus 3. And the way you would do that is similar, using this long division. And I'll give you the answers, but not the details in this case. So there's 4 possible solutions. Our next problem is determine all natural numbers n, so positive integers n, such that 4n squared plus 1 is divisible by both 5 and 13. I'll give you an example of one solution. If n is 4, then you have 4 times 4 squared, which is 64, plus 1 is 65, and 5 times 13 is 65, so we know 65 is divisible by both 5 and 13. The question is, however, to find all such positive integer solutions. So we'll start by dividing the problem into 2 parts. We want to see when 13 divides 4n squared plus 1, and then when 5 divides 4n squared plus 1. So in the first case here, 4n squared plus 1 is divisible by 13, when 4n squared plus 1 is congruent to 0 mod 13. And that's true when 4n squared is congruent to minus 1, just taking the minus 1 to the other side. And minus 1 is the same as 12 mod 13. Then we want to find the multiplicative inverse of 4 mod 13 and multiply times both sides of this. And it turns out it's 10. So 4 times 10 is 40, and that's 1 mod 13. So we get a 1 here. Then when we multiply 10 times 12, we get 120, and that's congruent to 3 mod 13. So we get this here. And then we want to find out what values of n, when squared, are congruent to 3 mod 13. So one solution is 4. 4 times 4 is 16, which is congruent to 3. And then the other solution is 9. 9 squared is 81. And 6 times 13 is 78, with a remainder of 3. So these are the 2 solutions for when you have divisibility by 13. And you can write that as n being of the form 13m plus 4 or 13m plus 9. Then we do the same thing here for 5. 4n squared plus 1 is divisible by 5, when 4n squared plus 1 is congruent to 0 mod 5. Then we can take the minus 1 to the other side, and then we recognize that minus 1 is the same as 4 mod 5. If we multiply both sides of this by 4, we get 16, and 16 is congruent to 1 mod 5, so we get a 1 here and a 1 here. And then we just need to find what values of n, 1 squared, are congruent to 1 mod 5, and one solution, of course, is 1. And the other one, which we just saw a minute ago, is 4 squared is 16, which is congruent to 1 mod 5. So these are the two solutions for divisibility by 5. And we can write that as n being in the form 5m plus 1 or 5m plus 4. So we want to know now, out of these possible solutions, when do you have divisibility by both 13 and 5? So we have 4 cases. We have the 13m plus 4 was either this case or this case, and then the 13m plus 9 was either this case or this case. So we have 4 cases, which I'll look at on the next slide. I copied the 4 cases here that I mentioned on the previous slide. We want to look at each one of those and see if both conditions hold. It turns out that both conditions hold in all 4 cases, but we need to prove that. So let's look at case 3 first. We have n being congruent to 4 mod 5 and n being congruent to 4 mod 13. So that means that n minus 4 is congruent to mod 5 to 5, and n minus 4 is all congruent mod 13. And so that gives us that n minus 4 is divisible by both 5 and 13. Since 5 and 13 are relatively prime, it must be that 5 times 13, which equals 65, divides n minus 4, which implies that n is congruent to 4 mod 65. So this gives us an infinite number of solutions. This fact here about two numbers each dividing another number, and if these two numbers are relatively prime, then their product divides the number, in this case n minus 4. That's a general theorem that I'll prove a little bit later. In fact, I'll state it as a problem, and then I'll prove it for you. So let's look at case number 4. From the second condition, we see that n is congruent to 9 mod 13. And then the first condition we can rewrite slightly. This implies that n is congruent to 4 plus 5 mod 5, which is congruent to 9 mod 5. So since n and 9 are congruent modulo 5 and 13, which we just showed here, and the GCD, their greatest common divisor is 1. In other words, they're relatively prime, which is what I mentioned before. Then their product, which is 65, divides n minus 9, which implies that n is congruent to 9 mod 65. So this gives us another infinite set of solutions. Let's go to the next slide, and I'll analyze case 1 and 2. Let's look at the other two cases. Case 1 I copied here. We want to find n that satisfies both of these conditions. If we look at the second condition, we see that that also implies that in addition to 4 being congruent to 4 mod 13, which is obvious, it's the same number, but you can add 13 to this and get 17. 17 is congruent to 4 mod 13 and 30, 43. Keep adding 13. 56 turns out to be the one that will work for us, in the sense that n is, in this condition here, is also congruent to 56. So from this first one here, we see that n minus 56 is divisible by 13 effectively. And if we examine the first condition, we can write n is 5 times 11 plus 1. We just have the 1 here, and this is essentially 0 mod 5. Then we add this together, and we get congruent mod 56. So in this case here, we got n minus 56 is divisible by 5. So since n minus 56 is divisible by 5 and 13, and 5 and 13 are relatively prime, their GCD is 1, we know that their product, 5 times 13 equals 65, divides n minus 56, and that gives us that n is congruent to 56 mod 65. So this is yet another infinite set of solutions. Then finally we look at case 2, which is very similar to this case here. We consider the second condition, and it turns out here that 61 will work in both cases. So I'm just adding 13 to 9, 13 again, 13, and we get 61. You just have to check some of these to see that that works out. It's not, I don't want to give you the impression it's immediate obvious, but if you look at 61, we see that n minus 61 is divisible by 13. And then we consider this case here, and we can write n is 5 times 12. This is 0 congruent mod 5, so we can add this in, plus 1, that's the 1 here, and that equals 60 plus 1, or 61, which is congruent to 1 mod 5. So in this case here we have n minus 61 is divisible by 5. So we have that n minus 61 is divisible both by 5 and 13. And using the same argument before, since these two numbers are relatively prime, their product divides n minus 61. And so we have n is congruent to 61 mod 65. So yet another infinite set of solutions to our problem. So the natural numbers satisfying the condition are those congruent to 4, 9, that was from the previous slide, 56, and 61 modulo 65. And we can write that as n congruent to plus or minus 4, plus or minus 9 mod 65. Notice that the minus 9 gives us the 56, and the minus 4 gives us the 61. It's just a more compact way of writing it. And then if you want to kind of expand it out, we can also write it this way here. The set of solutions are n of the form 65k plus 4, 65k plus 9, 65k plus 56, this one here, and 65k plus 61, this one there here, and that's for k in the natural numbers, so k being a positive whole number. So you may have one remaining question. We've analyzed these cases, and especially these cases 1 and 2, we found these numbers that worked and gave us an infinite number of solutions. But the question is, are there any more? Are these solutions unique for the cases 1, 2, 3, and 4? And I have a little bit of an explanation of that on the next slide. On this slide, I'm going to show uniqueness in case 1, and a similar argument I'll show for the other 3 cases. And this will prove that we've found all the solutions. So in case 1, we had that m was congruent to 1 mod 5, and m was congruent to 4 mod 13. And as you recall, we found that n equals 56 worked. So assume there is another number, let's call it m, that also works. This implies that m satisfies these 2 conditions. So m equals 1 mod 5 and m equals 4 mod 13. If we subtract the 2 solutions, then we have n minus m is congruent to 0 mod 5. So the n minus m is divisible by 5. And we have n minus m is congruent to 0 mod 13. So that implies 13 divides n minus m. And since 5 and 13 are co-prime, relatively prime, in other words, they share no common factors other than 1, a number that is divisible by both must be divisible by their product, which is 65. Therefore, n minus m is a multiple of 65, or n is congruent to m mod 65. So this proves that any other solution m is just 56 plus multiples of 65, but that was the solution we described for case 1. Remember, it was 56 mod 65. So nothing new comes out of this here if we assume another solution. We just fall back into the original solution. And so that proves that we have uniqueness in case 1, and you can do something very similar for the other 3 cases. On this slide, I have a theorem I mentioned a few times in the previous problem, and I thought I'd give you a proof. I was going to leave it as a problem for the listener, but I realized there was an identity used in the proof that you wouldn't have seen before, so I decided to just go ahead and prove it. We'll see this identity that I'm talking about in the next lecture that I'm making available after this one. So it's quite a useful identity. But what I want to prove here is that if the GCD of two integers is 1, which is known as being relatively prime, and A divides N and B divides N, so everything here is an integer, then the product A times B divides N. So as you recall, we've used this several times in the previous problem. So how do we go about proving this? First off, since A divides N and B divides N, we can write N as A times some integer K sub 1, and N also is B times some integer K sub 2. Then this identity, Bezout's identity, is what we need to do the proof here. It says if the greatest common divisor of A and B is 1, which we have in our statement of the problem, there exist integers x and y such that ax plus by equals 1. And that gives us pretty much what we need to prove the theorem. We multiply both sides by n, and we get this. And then moving over here to the right column, we make substitutions of these two equations here into this. So we put in b times k sub 2 for n, and then a times k sub 1 for n again. And then you notice here we have an a and a b, and everything's commutative here, so these are just integers. So we have ab here, and we have an ab term here, so we can factor that out. Then we have ab times k2 times x plus k1 times y, and that equals n. But then this is what we were looking for, right? We have an integer. These are just the product and sum of integers. So we have an integer times ab equals n, and that by definition says that ab is a divisor of n, which is what we wanted to prove. Our next problem is as follows. Determine all natural numbers n, so positive whole numbers, such that 169 divides this expression here, 3 to the 3n plus 3 power, minus 26n minus 27. So let's try to break down the expression on the right. First, we'll look at 3 to the 3n plus 3 power. We can factor the 3 out of the power here, so this is the same as this. Then we have this equaling this here. And then this is 27 to the n plus 1. And we can write that as 1 plus 2 times 13 to the n plus 1. Then we can use the binomial formula to write this out. So it's 1, then n plus 1, choose 1, which is just n plus 1, 2 times 13. Then n plus 1, choose 2, times 2 times 13 squared. Then it would be n plus 1, choose 3, times 2 times 13 cubed, and so on. But 2 times 13 squared is equal to 4 times 169. So that's divisible by 169. And the other terms have even higher powers of 2 times 13, but that they would also be divisible by 169. So all of these later terms in the binomial expansion here are congruent to 169, so they drop out as just being 0 when you're looking in terms of mod 169. And so you just have 27 to the n plus 1, and it's just these terms here that are not 0 mod 169. So that's what I've written here. I just multiplied the 2 times the 13 to get 26. And then we had the rest of the expression that we wanted to show 169 divides into was minus 26n minus 27. So if we put this and this and this together, this was the original thing we wanted to divide into, with slightly modified now because of the we wrote this in terms of 27 to the n plus 1 power. So we have this here. Then we'd write this in terms of this. And again, we're working mod 169. So we plug this in here. We get a lot of cancellation. The 26n and the 26n cancel each other out. And then you have 1 plus 26 minus 27. So everything cancels out. So this here is congruent to 0 mod 169. In other words, if we plug back in our original 3 to the 3n plus 3, we have this expression is congruent to 0 mod 169. In other words, 169 divides exactly this expression here, which is what we wanted to prove. This problem involves a technique that we're going to need for the following problem. I'll show you the solution on this slide, so you may want to pause the video once I introduce the problem, and then I'll give you the solution. So what is the remainder of 2 to the 500 power divided by 23? And again, if you want to work on it, just pause the video here. Otherwise, I'm going to proceed and show you the solution on this slide. So the trick is to compute it for a smaller power of 2 and then keep squaring it. So if we take 2 to the 8th, that's 256, which is 11 times 23 plus 3. But then this first part here is 0 mod 23, so it's just 3. And then we can square both sides, and we get 2 to the 16th power equals 9 mod 23. Then we square it again, and we get 2 to the 32nd power and 81. But 81 mod 23 is 12, or the remainder is 12. Then we do it again and again. I won't torture you with the details, but you just keep squaring it until you get to 256. And if we did it one more time, we would get to 512. So it's more than the 2 to the 500. But what we have in all these terms here is sufficient to compute 2 to the 500 and find the remainder when dividing by 23. So we write 500 as this sum here: 256, 128, 64, 62, 16. 2 to the 4th is 16, which is 16 mod 23. We didn't actually start with that. We could have, but I didn't do that. So we take 2 to the 500, and we can write that as just the 2 to these different powers. And when you multiply these together, you add the exponents. So these two things are the same. But we have the remainders for all of these. We have 8, 13, 6, 12. You notice 8, 13, 6, 12, 9. And then, as I say, 2 to the 4th is 16. So that has a remainder of 16 when divided by 23. Then you have a little bit more work to do here to reduce this down. I mean, you could multiply these together and divide by 23 and see what the remainder is. It turns out to be 9, but if you just want to do it with pencil and paper, you could work a couple at a time. You can find out what the remainder of 8 times 13 is mod 23, and then 6 times 12, mod 23, and 9 times 16, mod 23, and then continue working it down until you'll see that it's 9. So there's a little bit more work here to determine the remainder as being 9. So this is a general technique. We'll need it to solve the following problem, not this exact thing here, but this general idea. And the other thing I want to mention is when you compute these up to, in this case, 256, we can get everything, we can get any number 2 to any other number less than 512. So if we had, like, say 133, and we want to know what 2 to the 133 is, we would just write 133 in binary in terms of the powers of 2, and then we would just go back to our computations. We wouldn't have to do them again and do a similar calculation as to what we've done here, except you'd have a different set of exponents. Okay, so that was it for this problem. I have one more problem in this lecture, which we'll take a look at in a second. I decided to write out the last little bit of the previous problem where I had mentioned we needed to do a little bit more work to find 9 here. So if you recall, it was 8 times 13 times 6 times 12 times 9 times 16. So what I was saying verbally, I'm showing here, we can just find the remainder of 8 times 13 mod 23, and it's 13. And then 6 times 12 is 72, which has a remainder of 3 mod 23. And then 9 times 16, 144, that is a remainder of 6 mod 23. And then we just take the 13 times the 3 times the 6, and we get 216. And then the remainder of that mod 23 is 9. So just to complete the thought from the problem we had been working on. So let's go to the last problem in this lecture. For the last problem in this lecture, we want to show that 19 divides 2 to the 2 to the 6k plus 2 power plus 3 for every natural number k. And you need 2 theorems, or you could at least use 2 theorems to prove this. One is called Fermat's little theorem, and it says if p is a prime number, in other words, a number only divisible by itself and 1, then for any integer a to the p minus 1 is congruent to 1 mod p. And I have an example here. If we took p equals 5 and a equals 6, then we have 6 to the p minus 1, 6 to the 4th equals 1296, and that's congruent to 1 mod 5. And then there's another theorem, the least common multiple property. If n is a number divisible by integers a and b, then n must be divisible by the least common multiple of a and b. And this is just writing it in terms of notation. A divides n and b divides n implies the LCM of a and b divides n. Okay, so if you want to try this, pause the video here. Otherwise, I'll give you the solution on the next slide. I copied our problem from the previous slide, put it up here. And so this is equivalent to 2 to the 2 to the 6k plus 2 plus 3 being congruent to 0 mod 19. This is just taking this and writing in terms of modular arithmetic. And then we can take the 3 to the other side and get minus 3. And that's, of course, congruent to minus 3 plus 19, mod 19, which is 16, or 2 to the 4th. Next, we make use of Fermat's little theorem with p equals 19 and a equals 2. And we get 2 to the p minus 1, 18, is congruent to 1 mod 19. This tells us that powers of 2 repeat in a cycle of 18 mod 19. So every time we get to 2 to the 18th, we go back to 1. and that reduces the problem to a simpler problem. So to determine the value of 2 to some exponent e mod 19, we only need to determine the value of e mod 18. In our case, our exponent is 2 to the 6k plus 2. And we'll divide this into two problems. We'll evaluate this mod 2 and then mod 9, since 2 times 9 is 18. And then we'll put the result back together using the LCM property that I mentioned on the previous slide. So first we look at 2 to the 6k plus 2 mod 2. And that's the same as this is equal to this here, which is equal to 4 times 2 to the 6k. And since k is greater than or equal to 0, this number here is a multiple of 4. In other words, it's even, which means that 2 to the 6k plus 2 is congruent to 0 mod 2, or 4 mod 2, which is just adding 2 and 2 twice to 0. And I want to use this 4 rather than 0 because of the result we get in this analysis mod 9. You'll see what I mean in a second. So if we take 2 to the 6k plus 2 and then we evaluate it mod 9, first we simplify this. So we get 2 squared times 2 to the 6k, which is 4 times 2 to the 6k. And then 2 to the 6th is 64. And so that's 1 mod 9. Remember, 9 times 7 is 63. And so you just have a remainder of 1 relative to 64. And so 2 to the 6k plus 2 is this term here goes to 1, and so it's just congruent to 4 mod 9. So you can see here why I wanted to use 4 rather than 0. Now we have both 2 to the 6k plus 2 congruent to 4 mod 2 and 4 mod 9. And since 2 and 9 are relatively prime or coprime, means the same thing, just a different word, then we can use our LCM property to say that 2 to the 6k plus 2 is congruent to 4 mod 18, or equivalently 2 to the 6k plus 2 equals 18n plus 4, where n is some integer. We don't care what exact integer it is, but it's some natural number, some whole number. Okay, then we take this result and we put that back in our initial problem written in terms of modular arithmetic. So we get this here equals 2 to the 18n plus 4 plus 3. Then we can break this up into 2 to the 18 to the n power times 2 to the 4th. 2 to the 18, well, we've computed that earlier. Up here, it's 1 mod 19, so we get 1 to the n, and then times 2 to the 4 is 16, plus 3. And then you have, this is 1, of course, and you have 16 plus 3 is 19, and 19 is congruent to 0 mod 19, which is what we wanted to prove. Okay, so that was it for this lesson. I have another lesson on divisibility, and then I have several more lessons on the same topic of number theory, but different aspects, things like prime numbers and relatively prime numbers and so forth.